Hi everyone, my name's Alex. I work at Unity in the labs department, and today I'll be talking with you about the work of the Barracuda team, which is running neural networks in a real-time game engine. So first, I'd like to give a few words about Unity Labs, who we are and what we do. So the labs team is a research team here at Unity, focused on exploring how games and real-time experiences will be created and played in the future. Our areas of focus include game offering. How can AI and deep learning be leveraged to help out on the game offering front or simply to improve real-time experiences? A lot of work is being done on computer visualization, XR, and storytelling. At Unity, we see and really believe that neural networks are going to play an ever-increasing role in real-time content, be it to help out generating those contents or simply enhancing the real-time experiences. Therefore, we really want to give the ability to our users to run neural networks in a real-time setting. So the mandate of the Barracuda team is to implement a lightweight inference engine, which is fully cross-platform on all the platform Unity supports, as well as being able to run both on the CPU and GPU. We deliver it as a Unity package. It's fully open source and available on GitHub if you want to take a look at it. All right, so why do we do this, you might ask? The real reason is that we really believe that the machine learning and game dev communities are really powerful together. Be it to use machine learning to enhance your real-time experiences, or to use the power of a real-time engine to improve your AI applications. So the agenda for today's talk is pretty straightforward. First off, we're going to talk about all the different use cases for real-time deep learning inference in a real-time setting. Then we'll look at the overall pipeline we need to approach in order to make that a reality. And then finally, we'll look under the hood at all the different optimization that we need to do in order to make running neural networks in real time a reality. And then we'll wrap things up with some considerations and conclusion. All right, so we see a lot of different neural networks for different types of use cases on a day-to-day basis at Unity. However, most of these models can be pretty easily divided into two distinct categories. The first of which is medium computational intensity models. These models tend to be better suited to run on the CPU for a few reasons. The first of which is they tend to interact with other CPU-based systems. So think of a neural network outputting animation keyframes, for example. Well, these keyframes need to be read by the animation engine, which runs on the CPU. Therefore, to achieve very low latency, those two systems need to run on the same pipe. One other reason is that those models tend to be fairly complicated. When I say complicated, think of a wide branching structure, maybe some complicated ops, or some recurrent layers, all of which makes scheduling such models on the GPU not that efficient. Hopefully, generally, the input sizes of such models tend to be quite small. Think a few animation keyframes or a state vector. That means that the flops needed to execute the model is not that high, and the CPU can more than easily handle the workload. On the other hand, whenever we're dealing with models manipulating images, those models tend to be inherently better suited to run on the GPU. The first reason is that images tend to be quite large and are on the GPU pipe. Therefore, downloading them on the CPU doesn't make much sense. Another reason is that those models tend to have a lot of convolution layers, which are pretty computationally computationally difficult and are inherently better suited to run on the GPU. So now I wanted to look at a few different examples and of the types of models we see on a day-to-day basis, and which of them falls into one of the two categories. So the first category, the first popular models we see relating to medium computational intensity models are decision making or linked to decision making and agent behavior, as well as animation synthesis. For decision making in agent behavior, the question we're trying to answer is the following: Can AI and reinforcement learning be used to train and come up with smarter and better AI bots? The answer to this, we really think at Unity, is yes. This is why we have another Unity package called ML Agents, which allows ML practitioners and game developers to train efficiently very smart and powerful AI bots. So if that sounds interesting to you, the good thing is that ML Agents 2.0 just came out, and I put the link in the description, so if you can so we can take a look at it. Another really powerful use cases of neural network is animation synthesis. So it turns out that neural networks are very powerful at understanding natural poses and therefore drive a skeletal mesh. In this slide, I'm showcasing some work done by another team at Unity Labs called the Deep Pose team. And they came up with a new neural network architecture called ProtoRes, which greatly helps in the animation process, therefore greatly reducing the authoring time as well as improving the animation fidelity. So if that sounds interesting to you, again, I put the link in the description. Don't hesitate to take a look at it. As I mentioned before, for highly computational intensive models, they all tend to relate around manipulating images. The most flashy one would be style transfer. This model is pretty straightforward. It takes an input image, generally pretty large, applies a number of convolution operators on it, and at the end, we get a stylized version of the input. For XR tracking and segmentation, the process is roughly the same. You take an input image, you apply a number of convolutions, and you get at the output the segmented mask of the object you're trying to track. For object detection and tracking, here's the same, but in this case, you might want to fetch data on the CPU to analyze them further down the pipe. For object tracking, it's exactly the same. Another very interesting use cases of neural networks that we see at Unity is that we believe that neural networks can help our users really enhance the loading and enhance their application at loading or authoring time. For example, you can imagine neural networks being used to compress and upscale textures efficiently, or even to denoise backlighting data. So now that we saw that neural networks were very powerful in a real-time context, let's take a look at how we actually achieve it. So here I'm showcasing to you the pipeline that the Barracuda pipeline. So the user sits in Python and do their training with their favorite ML API, be it TensorFlow, PyTorch, or Keras. Once they're satisfied with their training, they can export their model to Onyx representation, which is an open source representation of the trained model. Then they can drag and drop that model directly into the Unity editor, where we will import it. And then they can use the Barracuda API to schedule that model in real time. Diving into a little bit more detail, as I mentioned, the user starts in Python, finishes their training, export their model to an Onyx representation. Onyx is an open source representation of the neural network graph. There's a pretty big community over on GitHub, and all the AI frameworks support exporting to that intermediate format, which makes it a very good choice. Once that is done, the user can then drag and drop the model into the Unity editor, where we will import it and convert it to our internal Barracuda representation. This representation is almost a one-to-one mapping to Onyx with some different granularities for legacy or performance reasons. Once that is done, we're going to have a compiler-like based approach, whereas we're going to apply a number of successive optimization passes to streamline the model and to make it real-time efficient. Once that is done, the user can then use the Barracuda API via the Barracuda worker to schedule the model on the different backends they want. For CPU backend, we leverage the Unity Burst compiler to compile our C# code to highly efficient vectorized SIMD native code. For the GPU pipe, we usually use compute shaders to target the different platforms the user wants. For a platform that does not support compute shaders like WebGL, we're about to release a pixel shader worker. The good thing with this pipeline is when we're going to add support for DirectML or NNAPI, it'll plug right in. As in, we're going to have a new backend a new worker where under the hood we will call all the interops of this API. So as you can imagine, simply importing an Onyx model and then coding all the different operators is not enough to make that model run in real time. As a matter of fact, there's a number of optimization that we need to perform under the hood to make those models runnable in real time. So the first types of optimization are focused on the model architecture itself. So here we're gonna trim down, analyze, and optimize the model on an architecture level. So trim down some nodes and simplify it to make it as streamlined as possible. But even that is not enough. We really need to focus our implementations on an operator level and really optimize our implementations and design them per backend. All right, so here I've shown you a dummy model on the right, which would be a model we would get from importing an Onyx file. And now we're going to look at the different optimization passes you might want to run on the model to make it more efficient. The first one of which is pretty obvious is your model might contain some layers which all their inputs are constant. In this case, there's no real reason to keep them around and execute them at runtime when they can be baked down at compile time. Similarly, your model might contain successive linear operations. For these layers, there's no need to keep them around when they can be merged into a single layer. Usually, memory operations tend to be more power hungry and less efficient than simple math. Therefore, wherever we can, we try to remove unnecessary load and store operations. In this case, there's no real reason to execute the convolution, store to disk, read again, execute the ReLU, and then write back again. We can do that into a condense operation. This one is pretty trivial, but we also simplify no-ops and simplify layers where we can. This optimization passes is a bit more tricky, but let's remember that the user are exporting their models from different neural network APIs. All of these APIs have different preferred tensor memory layout for the different layers. This will introduce at the end of the export process many different transposes throughout the model to match those memory layouts. Those random access nodes are not efficient at all, and we want to trim as much as we can to not have to execute them at runtime. So here would be the final representation of the model we would get after all of the passes, and would be what would be represented by the Barracuda intermediate representation. So you can see we go from the model on the left to the model on the right. It's a much more streamlined, efficient model, right? So one would expect a large performance win. But in practice, it really depends on the model architecture itself. As you can imagine, in this case, if the convolution were to take 95% of the runtime speed, the best we could win with all of our optimization passes is at most 5%. So really, it really depends on the model architecture itself. So here I've showcased different types of popular model architectures and the win we get by performing all of our offline optimization passes. As you can see for MobileNet, the wins are pretty substantial. We get a 27% win, which is really great. On the other hand, for EfficientNet, even if we do trim out a lot of layers, the real-time performance win is only roughly about 1%. So what does that mean? Well, let's take a look at what dominates the inference time and runtime. If you take a look at MobileNet, for example, convolution layers account for 80% of the total layer count, but account for 86% of the overall runtime cost. For ShuffleNet, it's even worse, whereas convolution layers account roughly for 30% of the total layer count, but account for 64% of the real-time inference costs. So clearly, removing layers and simplifying the graph is not enough when you have those very key computational heavy ops dominating the inference time. So therefore, we really need to focus our optimization and real-time implementations on these key specific ops. So let's take a look at how we go ahead and optimize them. For CPU matrix multiply, this one is a pretty well-known problem. In our case, we follow pretty closely in the works of Godot and Bliss, whereas we implement a parallel blocks matrix multiply. A few key takeaways here is that we do parallelize on the leading dimension of the output matrix, and the block size and inner loop size are all determined based on the architecture the user is targeting. For convolution, typically one would implement them via the M2-core algorithm followed by a matrix multiplication. This is pretty efficient because you can leverage the very fast matrix multiplication you've just coded in the last slide. However, here I want to dive a little bit more into details at what the algorithm does and see why it might not be as well suited as you think for a real-time context. So the M2-call algorithm works as follows. In this case, we're looking at for a 3x3 input image with 2 channels and a 2x2 kernel. So the 2x2 kernel is going to be slide on the input image. We're going to fetch a value, flatten them, and concatenate them to make the matrix on the right. So we do this, we slide, we concatenate, we slide, we concatenate. Finally, getting the middle matrix in the middle of the slide. Once this is done, we can simply do a matrix multiply with the filter kernel and get the output of the convolution. So that seems pretty efficient. However, when you take a closer look at it, in our example, for example, you can see on the right, the number 5 is repeated 4 times, and the number 6 and 8 are repeated 2 times. So that is a lot of memory overhead. In fact, if you have a k by k kernel, the memory overhead of the M2-call algorithm is k by k memory overhead. So this obviously is not very good, especially if you're targeting mobile devices where you're working with a limited amount of memory. It can go even so far as if we allocate too much memory, the API can kill our application. So we really need to be careful about the amount of memory our worker allocates. Therefore, in our case, we can't use the M2-call algorithm for memory bandwidth purposes. In our case, we use a custom variation of the M2-call algorithm, which is roughly as fast as the default algorithm. However, has a much better peak memory. So the way we do it is we implement convolution with k by k independent matrix multiplications. So at each filter index, we're going to copy a strided version of the input image, flatten the spatial dimension, and then do a matrix multiply with the filter kernel. We'll repeat that for the whole kernel, and then accumulate down the result to get the final result of the convolution. So this algorithm is really good because it does not introduce any memory overhead, since we're just copying a strided version of the input image. On the flop overhead, it's not that bad because generally the spatial dimension is much larger than the filter kernel. We use our C# code is compiled for the different backend we're targeting via the burst compiler. The burst compiler is another Unity package and is a compiler based on LLVM to compile a subset of C# into highly efficient vectorized SIMD native code. So you can see here our matrix multiply job being compiled for ARM v8, and at the end we get highly efficient assembly ARM code. Our CPU code is also designed to be heavily threaded and asynchronous. You can see here our M2-call algorithm spawning the different k by k independent matrix multiplications, as I mentioned, on all of our independent worker threads. So with all those optimizations, that means we can run efficiently a lot of different neural networks on the CPU. However, when handling models which manipulate images, running on the CPU is not enough. Therefore, we need to focus our attention to the GPU. The good thing is that for those models, the really computationally heavy layers all tend to be convolutions. So let's take a look at how we optimize convolution on the GPU. So on the contrary of CPU, GPU vary greatly across all the different hardware we're targeting. If you take a simple look between desktop GPU or mobile GPU, the landscape is vastly different. For desktop GPU, all of them have physical LDS. On mobile, is usually not the case. On the other hand, mobile has much better SIMD registers. Of course, depending on the different hardware, the number of threads needed to saturate the GPU and to hide latency efficiently will vary greatly. Therefore, what that means in practice is that we need to have many different implementation for very specific purposes and hardware. Our GPU convolution follow pretty closely in the footstep of our CPU one, whereas we're implementing our convolution via k by k independent matrix multiplications, followed by an accumulation. In this case, we don't necessarily do those math modes in parallel. They are simply unrolled in the shader. This is not as bad as you think because we do benefit from caching the input image. We did implement Winograd implementation for convolution. This provided a win on 3x3 kernels on some architectures. However, for larger kernel sizes, it can get pretty slow due to too much registers and LDS use. For LDS, even on architectures that do not have physical LDS, like ARM, it still provided a win. The reason for that is that the access pattern on the LDS memory and the size of the memory we allocate is not that much. Therefore, the GPU can better cache it. On the other hand, the number of threads and the block size and inner loop size, those are really dependent on the architecture. In this case, you really want to balance the number of registers and memory operations you do per thread. One other thing to consider when optimizing an algorithm is you have to pay attention about how your data is laid out in memory and how you're fetching that data. So you really need to be careful to match the memory access pattern, which is the most optimal for the hardware you're targeting. For desktop GPU, where all the threads, where the GPU is really efficient, if all the threads are accessing contiguous memory, a channel first layout of your tensor proves to be the most efficient. In this case, H and W are contiguous and channels are one after the other. On the other hand, if your hardware has TPU or actual silicon implementing matrix multiplication natively, in this case, you want to favor a channels last approach, where C is contiguous and H and W are one next to each other. On mobile GPU, you want a hybrid of the two, whereas you're still in channels first with contiguous spatial dimension, but have 4 contiguous channels to leverage the fold forward memory access. So here I want to showcase the different wins we get from channels first versus channel last on the different architectures. So you can see there's no clear trend here. It's really model dependent. On some architecture, channels first is better. On some other architectural, channels last is worse, and so on and so forth. So it really depends on the model itself and the architecture you're targeting. Here, I wanted to add an extra slide to showcase that being worse on channels first does not adequate to worse performance. In this case, I'm comparing some popular modern architectures on ARM and Qualcomm. I did correct a bit the gigaflops to make up for GPU generation gap, but you can see there's no really generalized conclusion. In a lot of cases, ARM is simply better than Qualcomm, but in some other models, these models are better suited to run on Qualcomm hardware. Therefore, there's no really generalized conclusion and is mostly dependent. Ideally, you want the model to target the hardware you're targeting. So one last thing relating to tensor memory layout is that one really needs to remember where we're coming from. So if you recall, our users are exporting from different neural networks API. All of those APIs have preferred tensor memory layout. So PyTorch is channels first. TensorFlow and Keras tend to be channels last. Onyx is channels first. So during all the import processes, there's going to have a lot of transposes in the model. And these random access nodes are really not efficient, and we don't want to be swizzling the data around in memory at runtime. Therefore, the approach we took at Barracuda is to trim out all these transposes where we can and have a fixed tensor memory layout. Then provide to our users the ability to switch between tensor memory layout from channels last to channels first. This is purely internal and decided at the worker level. There's no need to re-import the model. And how we do it is we swizzle the data when uploading it to the GPU. All right, so the cool thing with all those optimization we've just gone through is that real-time object segmentation on mobile is really right at our fingertips on newer devices. Real-time object detection on mobile is already being used in a lot of production, so that's really exciting. One thing to keep in mind is that here we focus a lot of convolutions on convolutions and convolutional-based layer models. However, model architectures are always evolving. There's always new and better and more popular models coming up every day. Today, we see a lot more transformers, and these transformers tend to have different bottlenecks and different layers and convolution-based ones. So it's really important to keep in mind what you need to optimize for the application. A really cool trend we see is that TPUs are becoming ever more present in newer devices. All that means is that going forward, our users are going to be able to run more and more different types of network and more powerful networks in a real-time context. At Unity, we really believe the world is a better place with more creators in it. So the more power and the more tool we give to our users, the better their real-time experiences will get. So really can't wait to see what people come up to and build. All right, so that concludes the talk. I hope that was interesting to you. If you're interested in knowing more about Barracuda, I put the link of the GitHub and feel free to go ahead and check it out. I'd like to give some thanks to the Barracuda team for their hard work, and especially a huge shout out to everyone at ARM here for organizing this event. So thanks a lot for tuning in and have a great day. Bye bye. There's a live Q&A session starting now to continue the conversation. To take part, join us on Zoom by clicking the yellow button just below the video player on this session's page.